Alright, in this video we're going to review how to solve for the general solution to second order differential equations. In other words, what we call the general solution. Okay, so here is our general second order differential equation, and so we have our second derivative term, our first derivative term, our function term, as well as the forcing function. Okay? And whenever you see an equation like this, what you're solving for is what we like to call the dependent variable, and often that's going to be the variable that's within the derivative. And so in this case, since we have derivatives in y, so we have d squared y dx squared, dy dx, and y, that's the one that we're going to solve for. As for all the other terms in this equation, we have the constants a and b, so those are just usually just numbers, and so think of 5, 6, 7, your favorite numbers. And the term on the right, that goes by a lot of different names, but usually in applied sciences like engineering, we call that the forcing function, because what you'll see is that in like a fluid mechanics class or like a heat transfer class, that'll be some kind of external factor that's causing your system to to respond. Okay, so first we're going to look at kind of the most simplest case, and so in the most simplest case, the only term that's going to be there is just the second order derivative, and so our first order derivative and our function term, those are going to be not there, and so in the end we get a form that looks like this, and so we have a second order derivative is equal to our forcing function on the right, and so this is very simple because we can just simply take this equation and just integrate it, and so our goal here is to solve for y. And so the opposite of derivatives is taking integrals. Okay, so let's go ahead and take an integral, our first integral here. And so if we take the integral of the left-hand side, we have integral of d squared y dx squared, and we integrate that, we get dy dx. So we reduce the power of the derivative by 1. And on the right-hand side, since we're just kind of doing this in general terms, we can't evaluate that integral there for f of x. And so I'm just going to leave that as the general integral of f of x dx. But the next part is really important, and so these integrals that we're taking are indefinite integrals, and so they don't have any integration bounds, no upper bound, no lower bound. And so in order to make this mathematically sound, we have to add an arbitrary constant to this, which I call C1. And the reason for that is that integrals are only definite up to a constant, if you don't have integration bounds. Okay, so we're halfway there, and so we took one integral, and so what we end up with is a first order derivative. And so if we take an integral again of the left-hand side, we take the integral of dy dx, then what we end up with is y of x, which is what we're looking for in the first place. Okay, and on the right-hand side, we're going to apply the exact same operation, and so we're going to integrate that entire expression. And what we get from here is, that first term with a double integral, it looks scary, but it only looks scary just because we don't know what f of x is. In reality, if you plug in a function f of x there, let's say you plug in f of x is equal to x, then you just take two integrals of it and you're good from that. And so we also have to integrate our constants there. So we integrate c1. Since c1 is just a constant, we end up with c1x. And then since, again, we're doing an indefinite integral, we end up with another arbitrary constant, c2. Okay? And so you might be asking, what are these arbitrary constants, c1, c2? So, this equation here isn't the final answer, and so in order to get a specific answer to this, we have to solve for c1, c2. But to do that, we're going to need to use boundary conditions, which is going to be the subject of the next video. But before we do that, let's go ahead and talk about the more general case when you have kind of this full second order differential equation here. Okay, so we've brought back the a dy dx and the by terms. Okay, and now we're trying to solve for the solution to this problem. Right, and so to solve these kinds of problems where you have kind of multiple terms here, not just the second order derivative, we have to form what's called the characteristic equation. And so you might have heard this before in a previous math class where you take each derivative term and replace it with the polynomial expression. And so second order derivatives will become a second order polynomial, and first order derivatives will become a linear term, just like that. Okay? And what you're going to do from here with the characteristic equation is you're going to find the roots of this characteristic equation. And you can do this, whichever way you feel most comfortable with. I know there's a million different ways under the sun. But what I like to do is I like to use the quadratic equation because that's, that gives you guaranteed the roots. And based on what these roots are, it's going to change what your solution looks like. And so we have three different use cases here. And so in the case when you have two real roots, in other words, lambda 1, lambda 2 are both real numbers, then your solution is really simple. And so your solution is just going to be y of x is equal to c1 e to the lambda 1x plus c2 e to the lambda 2x. Okay, and so we have two exponential terms. Again, with two arbitrary constants, and so that's going to be the theme for second order differential equations. If you have a repeated root, or in other words, you have just one root and it's repeated, then you're going to find your second solution here by multiplying by x. And so your first solution here is going to be c1 e to the lambda 1x. Then your second solution is also going to be c2 e to the lambda 1x, but we're going to multiply that by x so that we have two linearly independent solutions. Okay? And so the last situation here is if we have two imaginary roots, or in other words, two complex roots. And so in those cases, we leverage Euler's formula to get this sinusoidal term. Okay? So we have y of x is equal to e to the minus a over 2x times c1 cosine omega x plus c2 sine omega x, where omega here is b minus a squared over 4, where b and a are the constants from our original differential equation. And so that gets us most of the way there, but in the most general case, when you also have this non-homogeneous term, this forcing term on the right, you need to use some additional methods in order to solve that. And so some of those methods that you might have learned in your previous math classes would be something like undetermined coefficients. Another way is variation parameters, or if you've taken EGME-333, you probably have used Laplace transforms to solve these kinds of problems as well. And so that's a little bit out of the scope for this video, but I wanted to at least remind you of the different ways that you can solve for that so that you can look those up in your notes. And so that concludes this video about how to solve for the general solution for second order differential equations.